Join computer. Share screen. Sorry, I'm just setting this up for people who are in Zoom. They can try now. You guys, if you have a hard time seeing the slides, you can also use Zoom. Sometimes students do that. Okay, so here we are. Like this. Kind of crazy. Okay, what is an operating system? People have, it's a program that acts as an intermediary between a user of a computer and the computer hardware. We're going to see some more definitions, but what does that mean? Intermediary means, I don't think so. Intermediary means that I want to print something to the screen. If you remember from your course on, the truth is the course in Mivnei Machshev is very important because you connect. If you wanted to print something, you just type syscall. That's basically requesting the operating system to print something for you. What's hardware? Hardware is a screen. So if I want to print something, for example, give you an example. I'm not going to directly speak to the hardware. In other words, it might need certain certain codes, certain machine language instructions. All of that, I'd rather have an interface to it. And that's the operating system. So in other words, the operating system will know how to speak the language of every device on the computer. The device is another word for hardware. And I will know how to talk to the operating system. And he will act as an intermediary or translator. And that gives me what we call a level of abstraction. I'm recording. Yeah, I'm recording. That gives me a level of abstraction. In other words, what does that mean by abstraction? I can write a program that uses certain operating system calls, and it can run on two different hardwares, and it will work. Because I'm abstracted away from the hardware. I'm pulled away from the hardware. I'm writing in a kind of universal language, but it's specific to that operating system. As long as that operating system has been ported for that hardware, then I can use that operating system call. So it's kind of the same idea of a high-level language, which is also abstracted away from the hardware, as opposed to writing in machine language. So an operating system is an intermediary. That's what that means. It needs to understand what hardware it's running. That's why what we have is device drivers. They're called device drivers. A little program. What is a device driver? It's a little program that speaks to the device, to the hardware, allows the operating system to communicate with the device. Now, for example, let me explain a little bit about that, device drivers. If I make a new piece of hardware which I want to sell, it's my responsibility to write the device driver for each and every operating system that I want it to work, because he doesn't know my hardware. So I'll write a device driver which his operating system can then communicate with. And then the programmer will communicate with the operating system. The operating system will communicate with the device driver, which is essentially the device. The device driver is a small program, let's say written in binary, written in machine language, for the operating system to communicate to the device. When Windows 10 came out, they removed a lot of device drivers from Windows and Windows LT, whatever, from other Windows that was before Windows 10. And all of a sudden, old devices didn't work. Why did they do that? Because the operating system was getting bigger and bigger, supporting devices for the past 30 years. Every device driver that could ever be, they had it built into the operating system so that any device you plug in, it would work. He said, well, wait a second, let's remove half of the stuff. So now that's fine for everything that you bought in the past 10 years, but not for your old stuff. Now that won't work. The operating system said we no longer support those old hardware. And they did that and what that means is they removed the device drivers. So I just explained what intermediary is. Operating system go execute user programs that make the computer system convenient, use the computer hardware. In other words, everything you get out of Windows. In other words, you want to be able to run programs, you want to be able to use the computer. Let's go.
But I lost the USB.
Over there, but then you go. בסדר, בסדר. אני מלמד הבוקר, אז רציתי להגיד, סליחה. אז אפשר אולי בשתיים, אז משהו. אולי באחד, אולי אפילו באחד, אבל בוא. אוקיי. בסדר. אוקיי, alright, אוקיי, נדבר שוב. אוקיי, ביי. תודה, תודה רבה. Thank you, wow. Why I'm sitting here because I don't want to talk to the computer, and I'm not gonna put this over there. I don't. So, hardware provides basic computing resources. Okay, so we're now saying what is a computer conceptually? Computer is hardware, operating system. Look, first one's hardware, operating system, programs, like a word processor, and people, and 4 components to a computer. Computer won't work without people, right? As part of the conceptual idea of a computer, the users. But the point is, operating system is in there. Let's go on. So here you see that same thing. User, programs, operating system, hardware. It's just the same thing. But they're showing it. The hardware is like, I don't know why it's smaller, but it's inside. The operating system talks to the hardware. The operating system also talks to the programs, and the users talk to the programs. And there's examples of programs: compiler, an assembler, a text editor. You all know what those things are. Okay. What operating systems do? Users want ease of use, and they don't care about resource utilization. In other words, they don't really care whether the CPU is being used well or not well. They just want their own user experience to be good. Okay, that's not such an important point. But shared computers, or which used to be called mainframes because they were like the size of this room, and now I would just call it a server. I actually changed the slide there. It didn't say server, it said mini computers. I changed it to servers because mini computers is like an innovation of the early 70s everyone's excited about, but like It's so irrelevant now that I can't even have
What
it.
exactly? Like
Mainframes are just like old-fashioned servers, and servers are like modern servers. And what the point of them is that multiple users are on them, and there needs to be it's like, think of a computer as like a city with roads. You need a policeman to maintain order. Make sure you don't go into the house of somebody else. Make sure you drive on the road and nobody else. Like, it's your turn to drive on the road, so somebody else shouldn't be there. So the operating system has to maintain order between all of the different programs that are running on the computer. Right, there are different programs running on the computer. You can think about your course in Mivnei Machshev architecture. In that course, even though there was an operating system for the purpose of talking to the hardware, there was no operating system for the purpose of multiple users, managing users, or managing multiple programs, even multiple programs, right? There was just one program. Your program ran, and that program had all of the registers, right? And nobody else was going to start using the registers while you were using the registers. There was only one program running. If we're going to take one computer like we had in operating in Mivnei Machshev and say, no, let's put on 10 programs running simultaneously. So we're going to have to think about how to do that. We're going to run into certain problems. What if you're using my registers? Also, you're using the CPU and I want to use the CPU. We're going to get into lots of problems. So that's the goal of the operating system, is to turn what we did in our computer architecture, turn that conception of a computer into a modern computer where we have multiple programs running at the same time. That's the job of the operating system. Okay. Right. Some computers have little or no user interface, such as embedded computers in devices and automobiles. That's important. In other words, you should understand the concept of what an embedded system is. Embedded system means that it's specific to a particular machine. By machine, we mean a car. My favorite example is a fighter jet. He has, an airplane, has all kinds of computer systems built in, which are very specific in their nature. You can't take that and use it to calculate, something else. They're just designed to calculate missile launching and, I don't know, wing shape and, all the things that the plane needs. There are all kinds of systems. There are different computers in the plane that do specific jobs. Those are called embedded systems. They're small. They're essentially like, we call them, actually, they have system on a chip nowadays. A single chip, which is a whole computer. Cards, also cards. I think on my card there's like 26 computers, some more.
So an embedded system
Is a operating system designed to work with a very specific machine, as opposed to all-purpose operating systems. You know what I mean? Like Windows is just meant to work with the computer. I'm supposed to use the computer to do it. This computer is not designed to work, is not built to run a washing machine. It's built to do anything. I could maybe connect it to a washing machine and then tell the washing machine what to do. But it's not embedded in the washing machine. That's why it's called embedded system. It's not part of the washing machine. So those kind of have little, for example, another example is a handheld calculator. That's you can't make your calculator. You can only make it do what the buttons do. You can do multiplication, division. That's it. You can't program it. I mean, they have programmable countables, but a simple calculator is not a computer. Is an embedded system. It's a computer. It's totally a computer, and it's totally got an operating system, but it's an embedded operating system. It only does a limited number of things. It has a limited user interface. Here I added these two in underline. Protect and separate processes from each other. That's important. That's what I said about computer architecture. In that course, we didn't have multiple processes running. In a process again is a program while it's running. We only had one program. Give each process the feeling that it is the whole computer to itself. In other words, when I run a program, I shouldn't feel like I'm waiting for some other program to finish. It shouldn't tell me that, you got to wait now. It should give me the feeling that I'm running my program. Okay. Operating system definition. Okay, you could think of an operating system as a resource allocator, as I was saying, because it manages all the resources, like the CPU is a resource. Who gets the CPU? Or the registers. Remember the registers there. Very important. Remember the registers. The CPU only can manipulate what's in the register. So who's get to write to those registers? Decides between conflicting requests for efficient and fair resource use between processes. I have multiple processes. They both want to use the CPU. I've got to decide. I got to be the shoter. I got to be the policeman. Controls execution of programs to prevent errors. Also, I shouldn't be able to write the data or the code of another program. There has to be a clear division. Well, houses have locks on the doors. I shouldn't be able to write to the data of one program. Shouldn't write to the data of another. The data needs to be how do you call it? Integral. Has to be only theirs. Now we're continuing on the definition here. There's no universally accepted definition. But one definition is, here's 3 definitions. Can you guess the one I added? No, the third one, which says ND at the end.
I didn't see that part. I just saw it.
Yeah. Everything the vendor ships when you order an operating system. In other words, when you buy Windows, what do you get? That's the operating system. When you buy Windows, what's another operating system? Linux. If you buy Linux, you get different things. But that's a bad definition, really, because everything you get, you get maybe a calculator, maybe you get a notepad. Is Notepad part of the operating system? It's a program. Why is it part of that? So a better definition is the one program running at all times on the computer. That's a famous definition. That's the kernel. Everything, it's also, the kernel we'll see is like the kernel is like a seed at the center. The most important essential aspect of the operating system is called the kernel. Everything else is either a system program or an application program. In other words, everything else is programs, but there's one thing so that the one program running all the times. I don't like that definition because that definition doesn't describe it. So what is that one program? It doesn't give any information about it. It's like saying there was a famous thing that I don't know, Aristotle or Plato said that a man is a two-legged animal. That's what a man is. And then somebody said to him, but somebody, I don't know, this is kind of a joke. Somebody said, no, but a chicken also is two-legged animal. So why shouldn't a chicken, according to that definition? So he said, okay, man is a featherless two-legged animal. So they laughed. So somebody said, okay. So somebody walked out and came back with a chicken that he had plucked all the feathers off. Said, here is your man. Here is Aristotle's man, the featherless biped. But in other words, that a definition should not only differentiate it from other things. It should also tell us something about it. So this differentiates it, the one program running, but it doesn't tell us what the program does. So my definition is the one program that manages, controls, and provides services for all the other programs running on the computer. That's what we've been saying all along. It's the program that manages all the other programs, controls them, and gives them services. What do I mean services? Gives them access to the hardware. I think that's really a good definition.
Why do they give millions of definitions if you were able to sum up?
They're not as smart as me. I don't know. They may have some other reason. They want to have a short definition. It's like we're going to learn about processes and threads. So we call it process, which is a program, but we're also learn about threads, which is those like programs are composed of threads. And what the definition of a thread is a lightweight process. They just love to say that. A lightweight process doesn't tell you very much. What does it mean lightweight? So then under that heading, they can explain that. Sometimes definitions are just to try to be succinct. All right, what is a bootstrap program? There's a theoretical problem with a computer, which is the operating system is on a hard drive, and the computer is the hardware. Can you turn it on? How does it know where to read the operating system from on the disk? Maybe it's at the beginning of this, maybe it's the middle of this. Where is it on the disk? And how does it even know that there should be an operating system? Maybe you didn't put an operating system on your computer. You just have the hardware. So how does it know? Who's going to tell it? So there has to be another program which knows where the operating system is and jumps over there and it sort of tells the hardware where to copy program from the hard drive into the memory, right? Program can only run, very important point, program can only run if it's in memory. If it's on the hard drive, you cannot run it. It has to be in memory. So the bootstrap program is the program that copies the operating system into memory and runs the operating system. And you must have a program like that. Now, where is that program? It can't also be on the hard drive because then how do we know where to get it? So it's in a special kind of memory called, well, it was originally called RAM, read-only memory, which is sort of embedded in the hardware. But it's also called EEPROM, which is, we discussed this in operating in Mivnei Machshev.
So bootstrap program, it copies the operating system
To memory. And to do that, of course, it has to know where the operating system is on the disk. Nowadays, they have a triple state. That's 2 steps process. Nowadays, they have a triple step process where they want to keep the EEPROM, the ROM, very small, and it always reads to a certain section of the disk. And then on that disk section, you can tell it where the operating system is. And that way, you can change where the operating system is or have what's called a dual boot. You can in that small, in the section where the of the disk, which it always reads, you can write a program that says, allows you to choose, allows the user to choose, do you want Windows or Linux? And then he presses Linux and it'll read the section of the hard drive that has the Linux operating system in. So on your hard drive, you can have 2 operating systems. And anytime you start up your computer, you could choose which one you want. And that program, that first little program on the hard drive will actually be what's deciding, what's asking it. Yeah. Find what? To find? To find. I thought you said define. No, so the EEPROM is a program written in a binary, and it's in the EEPROM or the ROM is a program in binary, which was written by the person who built the computer, and that program tells it go to the byte number 0 in the hard drive, something like that. So he knows. So the EEPROM is a program that's been written. And actually, what is EEPROM? What's in ROM and EEPROM? EEPROM means that you can change it. ROM means it's read-only. You can never change it. EEPROM means electrically programmable read-only memory, which means you can, through certain manipulations, change what's written there and tell it, no, don't go to byte number 0, go to byte number 1000. So it's a program there. Does that answer your question? And it, no. EEPROM is the hardware, is a piece of, is like a disk on key. It's a piece of hardware. In it is a program called a bootstrap program. And that program does 2 things. It finds it and copies Yeah, Bootstrap does both. It finds it and writes it into memory. Why is it called Bootstrap? Because an expression in English, lift yourself up by your own bootstraps, which of course is a logical impossibility, right? If you fall in the mud and you say, "Can you give me a hand to get out?" and you say, "No, you lift yourself up." You can't really lift yourself up. Yeah, you try to lift your bootstraps so you won't go. But that's the idea here, because it's kind of impossible. That's kind of a conundrum. How can the computer know how to start itself? So this is the solution to that. So, all right, this is just how a computer looks. This is a conceptual description of a computer. Notice above on the top row is all the hardware. The hardware, so the disk talk to a disk controller. There's a CPU, which is built in. The gray is the essential, is the computer. The memory is something you can add to the computer, and how much memory is becomes part of this. The CPU reads the memory. Well, it actually really reads the register. Registers not in this picture because the registers are considered part of the CPU. The USB controller. Okay, those are the device drivers. That's what I was saying about device drivers. Graphics adapter. There's a graphics card in your computer. All these things that are all the gray and the blue could all be put on one chip, one integrated circuit. The first line here is very important. I/O devices and the CPU can execute concurrently. It's a very important point. That's gonna become relevant later on. In other words, the CPU does not have to be involved in reading from a disk. I can just say read from the CPU can say read the disk, and now it's going to go and take an hour to read from the disk or whatever. A long time, not an hour, but a minute is a long time, or 10 seconds is a long time. So it's going to read, and meanwhile, the CPU can do other things. So they can run concurrently. Each device controller is in charge of a particular device. Okay, I said that kind of, right? Yes, the CPU can sort of say, start writing. And then, the program will start writing. We're going to learn this as something, there's a specific device to help it do that. But basically, the CPU does not have to be involved in the actual writing of data to and from the hard drive or from the keyboard or to the screen. Those are all I/O devices. Well, actually, I take that back. The hard drive is a little bit different. Really, we're talking about the screen and the computer. So you can write to the screen. Writing to the screen is very slow. Reading from the keyboard is very slow. CPU doesn't have to wait for that to finish. You can just, okay. Each device controller is in charge of the device. Each device controller has a local buffer. Right. There usually is built-in memory. Buffer is memory for each hardware device. Because he doesn't write directly to the memory, he writes to a cache. We talked about in cache in computer architecture. So now we're going to say that the new thing we're going to say is that every device that connects to the computer has its own cache. And that speeds up things. He'll write to the cache, and then the cache can be read. So we call that a local buffer. CPU moves data to and from main memory to and from local buffers. Right. The CPU will copy from the buffer. Now, what we're trying to say is like this, that the writing to the buffer may be very slow. So the CPU doesn't want to wait around. Keyboard writes to a keyboard buffer. Finally, the guy finished typing hello world and hit enter. Now the CPU checks the buffer and says, oh, there's a full piece of data here, and it reads the whole buffer, hello world, in 1 second, and very quickly. That's why we have the buffer. Sort of mediate between the slow behavior of the I/O devices and the quick behavior of the CPU. I can give a mashal. It's like if you have some student who's like ADHD or something, and she can't sit in class. So she's like, she has to walk around and leaves the class, comes back. But meanwhile, her friend is writing down all the notes. And so as soon as she comes back in, she sees there's nothing on the paper, so she goes out. Then she sees her friend wrote a whole page of stuff. She comes down, sits down next to her friend, and quickly writes, copies over everything the friend wrote, and then goes out again. She can't be bothered to sit in class and doing, at the slow pace she's teaching. So that's the CPU. CPU is like an ADHD. It can't sit and listen. It has. Yeah. So we need a buffer. This is the friend of the friend of the student is that buffer, that local buffer. Here we go. Device controller. So the question is, the way I said it is that the girl keeps coming in to check if there's something on the paper. That would be called polling. Write that term down. We're going to come to it again. Polling. The definition of polling is to periodically check if something is available. I'm polling. In other words, I want to know, did people like Bennett? Do they still like Bennett? Every 2 days I do a POLL. POLL, right? POLL-ING. Like every day I want to know, is Bennett still loved by the country? So I do a poll. And every day, but I do periodically, every week. Some periodic period where I poll something to see if anything has changed. Nothing has changed. Nothing has changed. Now everybody loves him more. And now everybody hates him. So polling is periodically checking if something is available or ready. The other alternative to polling is called interrupt driven or interrupts. So interrupt means that that instead of the girl coming, the ADHD girl coming in on checking the paper all the time, whenever the girl in class finishes an amud, finishes filling up a page of writing, she shouts out to the door, "Come in, I got something for you." That's interrupt, because I'm interrupting her. She's busy playing ping pong in the hall. I interrupt her, and I send her a message, "Come and get, you can read the data." So that's interrupt driven. So what does this last sentence say? The device controller informs the CPU it has finished its operation by causing an interrupt. So what we're saying is that the device driver, he calls it device controller, you can call it device driver, same thing. I'll call it device driver. I think the device driver will, whatever, either term. Now I'm going to sit here and think which is a better term. The device controller will say, "Oh, I finished the page." It'll inform the CPU, come and read it, which is an interrupt. It tells the CPU, stop doing what you're doing. That's called an interrupt. Okay, we got a lot of material here. The problem is I like to explain that. And I think you know me for the mouse. Oh, Elon. Okay. Interrupt transfer. Okay, so now we're talking about interrupts. I already explained it to you. But interrupts transfer control to the interrupt service routine generally through the interrupt vector, which contains address of all this. Right, this is like more complicated than we need to know. Yeah. Maybe it doesn't. I don't know. Basically, what we're saying is that computer system operation. How do computers work? And the device driver. You're right. You're right. We don't have the operating system in the picture. We just seem to have the device driver telling the CPU. Well, how does it tell the CPU? Through the operating system. Now, when we say that the where this slide you're talking about? We're just saying an operating system is interrupted. The operating system sits around doing nothing until it gets a message to do something. For example, a device may say, I finished writing to a buffer, come and read it. That was just an example. But that's the operating system's job, is to sort of have a mechanism for sending and receiving interrupts, right? It has to be able to receive interrupts, these requests to do action. That's all we're saying. Was it? Everything is a CPU. Nothing happens on a computer that the CPU doesn't do. You know, essentially. Well, we're going to learn about an exception to that, but CPU is, you know, the operating system is a program. Remember we said that definition that I don't like? The one program that's running all the time. It is a program. It's a program running, which means it's using the CPU, which means that you're saying, how exactly does the interrupt get to it? That's what we're trying to explain here. Basically, the program has to be able to sort of call a function, sort of like calling a function of the operating system. There's like kind of a function call with a pointer to a certain space in the operating system. It says, do this. That's what the interruption is. Yeah. Exactly how that mechanism works, we're not really going to get it, but that's the basic. The operating system is sort of ready and waiting for various interrupts to come, and then the device driver will send an interrupt. It can send interrupts to, well, yeah, it can stop the program from running. But we're going to learn about that. It has to stop programs from running. Probably, yeah, I would say, yeah. Okay. Wait, where am I? Am I in the same form? Okay. Interrupt handling. So let's see what this says. The operating system preserves the state of the CPU by storing registers and the program count. Oh, did I skip a slide? Maybe I did. Yeah, let's go. Interrupts transfer control to interrupt service. We sort of did this. Interrupt transfers control to the interrupt service routine, generally through the interrupt vector, which contains the addresses of all the service routines. In other words, there's a set of interrupts of different things that the operating system can do, and that's there's a routine, service routines, and there's a vector, which is essentially an array of the name of the locations of the pointers to those functions. And the interrupt says, go do this function, go do that function, go do that. Interrupt architecture must save the address of the interrupted instruction. In other words, if I'm in the middle of a certain line of code and I get an interrupt, I have to know to get back to that line of code. So I have to save the address of that code in memory, where it was in memory. There's something called an exception or a trap, which is a type of interrupt, but it's a software interrupt as opposed to a hardware interrupt. What we talked about until now was the hardware saying, I finished writing on the paper. That I finished writing to the buffer, to the intermediate, to the cache. I finished writing to the cache. Come and read it. So come that was a hardware interrupt. But there could also be software interrupts, which are called exceptions or traps, which are usually by an error or an explicit call in a software. In my software, I can say, please do this interrupt. Operating system is interrupt driven. That's a key concept, which is that the operating system in general doesn't do it polling. In other words, he waits for requests to come. Hardware interrupt is like from a device, like a keyboard or something. I finished typing. A software interrupt is from an error or from the actual program. Like well, it's of course in Unix, third year, but you can actually request certain interrupt in your code. In my C++ program, I can say, do this interrupt. That would be a software interrupt. Hardware would be if the hardware itself talks to the hardware through the device driver, which remember the device driver is installed in the operating system. So he has direct access to the operating system. We're not really going to learn. I don't personally know how to write a device driver, but that would be a good thing to know how to do. That would be really understanding on a very low level how to communicate with the between the hardware and I have a friend who that's one of the things he does. But that could be a whole course, probably. I think, but I don't know. Okay, so the hardware interrupts are from the devices, from the keyboard, the screen. The operating system the operating system preserves state by storing registers, right? So this is a key idea. You have to store registers and the program counter. Remember, there's the PC, the program counter, what line I am in my machine language code. I need to keep track of them so that I can get back to my code. I also need to store all the values that are in the registers, like we did when we used the stack to store that. If I'm going to interrupt a program, I'll give you an example. Let's say the operating system is running a certain program that's printing hello world 1,000 times. And in the middle, it gets an interrupt from the keyboard. Stop what you're doing. Control Z on the Unix. It gets certain interrupt. A mouse click. Go to a different program. Stop the speed. Whatever he gets, whatever interrupt. Mouse click is also an interrupt. A mouse click is a hardware interrupt because the mouse is hardware and it's interrupting something, stopping you from saying, now do this. If I do X on a window, I've really interrupted it. It's in the middle of doing something and now I stopped it. But let's say I didn't stop it, I want to come back to it. I didn't kill it, I stopped it. So in order to be able to come, now the CPU is going to go do something else, which means the registers have to be available for that something else, because everything is through the registers. That's the only place that the CPU reads, registers. But the registers are busy with the hello world program. So I have to do the same thing I did in the functions in architecture class. I have to copy all the registers somewhere else. That's what's written here. That's called the state. The combination of the registers and the program counter is essentially the state, right? What's in the registers at this moment and where am I in the program? Because I could have the same, I could be at this line of the program, but I can be the 1,000th iteration of a loop or the 2,000th iteration of a loop. So to know my state, it's not enough to know what line I am in the code. I also have to know the register values. What's my I? If I incremented it to 1,000 or to 2,000. So that's called the state, although he doesn't write that here. Oh yeah, preserves the state. Determines which type of interrupt has occurred. Oh, I don't want to. Polling. Oh, here, I underlined this. I guess I added this. I don't remember. Once the interrupt occurs, so what's polling? Once the interrupt occurs, the system must determine, in other words, when an interrupt happens, we just described vector interrupt. Well, I'll start with vector. Vector interrupt, when the device interrupts, the system enters the interrupt acknowledge cycle, asking the interrupting device to identify itself. I added this. The device then responds with its interrupt vector. The kernel then uses this vector to find the responsible interrupt handler. So in other words, there's some kind of communication going back and forth. He interrupts the operating system, and the operating system sends him back a message. There's some kind of, that's a vector determining what interrupt is triggered. The other way is polling, where, yeah, do that me that service. Do me that service.
So just to sum it up, of interruption, basically.
Yeah, it's the key line actually is it asks the interrupting device to identify itself. That's the key line. As opposed to checking, are you the interrupt device? Are you the one that's requesting an interrupt? Are you the one? Somebody said to me, read the girl's out in the class playing ping pong. She gets a message, come and copy the paper. But from who? From girl one, girl two, there's 10 girls in the class. She has two choices. Either she can go and check every single girl until she finds the one who has the paper that she wants to copy. That would be polling. Vectored means she would shout back and say, please tell me if you're the one who requested my services.
My mother asking.
Saying, if you're my mother, shout. Yeah. That was a monkey, I thought.
What?
I know the version of the story with the monkey. Are you my mom?
No, there's
Oh. You don't know Julia Donaldson? When you they're famous English, they're like 1990s, 2000s children's books. Anyway, are you my mom? Yes. So, but I think the example is clear. Those are two ways. I think that vectored is the way we go nowadays. Anyway, I added this this is a little bit stuff that you're not really gonna have to know this so well. Okay. Separate segments of code determine what action should be taken for each type of interrupt. The main thing you should understand is what the heck is an interrupt, and that it's very different from sequential code. Right. This picture, a little bit hard to understand, but this is showing how I think that's all it is trying to show in this picture. Um, Good, I'm gonna have to go to the bathroom.
What exactly did you say? The one with the up and down.
So the only one,
One with what? Blue and orange.
CPU only.
Right, so actually what I just said in the previous slide is what's said here. After IO starts, control returns to user program only upon IO completion. In other words, when I said the CPU is available, but my program, I did like cin and I'm waiting now. And the guy is typing. And when he finally finishes, he hits enter. But that's called IO starting, that I'm waiting for him to finish typing. And even actually, he hits enter. I don't immediately get, it's not the, now the buffer, when he hits enter, now is really when IO starts. Now he has the job of reading from the device, whatever he typed, only when the enter comes does he know to start reading. Then he reads from the device into the buffer. And then when the buffer is full, then the CPU can actually start to read it. So that's what it says. After the IO starts, control returns to only upon IO completion. In other words, my program is not using the CPU now. Wait instruction idles the CPU until the next interruption. Right? There's a special instruction called wait, which tells the CPU not to do anything. You can't have simultaneous IO processing. In other words, when I type hello world and I hit enter, I'm either on this program or that program. I can't be on two programs at the same time, right? If I have two windows open, I got to click, I got to sort of, it's called the foreground. I've got to bring to the foreground or to the focus. So in Windows, it's called the focus. In Linux, it's called the foreground. I got to bring to the foreground the program that I want the typing to be for, right? If I have two tabs, each with a form, I have to know which form I'm filling out. So I got to see, you'll see the one that you want. That's called bringing it to focus. But it can't be simultaneous IO. That's sort of obvious. We're familiar with that. What about if I have two programs that are both writing to the screen and they're running simultaneously? And I have just like a black, well, really you should learn Linux, but I'm writing, they could actually write to the screen interleaved, but not simultaneous. Interleaved. Okay. A system call. Oh, wait. Well, I'm going to skip that. Here, DMA. So this, we actually remember. Do you remember this from operating from computer architecture? We talked about the DM. Did I teach you computer architecture? Or I just did the lab. Ah, so maybe you didn't have this because you had with Avi, yeah?
Yeah.
I don't know if you talked about this. So the DMA, it's in the Hebrew material. The DMA is a special piece of hardware that allows, you see, if you remember, how does a CPU copy something? It allows, I'm sorry, it's a special hardware. I should finish my sentence. Special hardware that allows for fast copying of data. What do I mean? If you remember in architecture, if I want to copy something from memory, I got to do a load word. And then the CPU will copy one word from from memory into a register, right? But what about, how am I going to copy from the hard drive into memory? What we did was we did from memory into a register. But how am I going to get from the hard drive into the memory? Right? The program is in the hard drive. I want to get into memory. And then I'll be able to run it, and then I'll be able to copy data. But how am I going to get it into memory? So if the CPU would do it, how would it do it? It would copy one word at a time. That's the only thing it could do. It would copy a word from the hard drive into, would have a device. There's a cache for the hard drive. So it would read from a certain amount of data would be written to the cache. Then it would read the data byte or word by word into memory. It would do a load word. How would it do it? It would do a load word from the cache of the device into a register, and then from the register into memory, one by one. And if you wanted to copy 100 megabytes, it would take you ages. So there's a special device called a DMA, which all it does is this job: copy from the hard drive into memory. And the CPU is not involved. It just tells it start here and here. Just tells the starting and stopping points. And then the DMA can copy a whole chunk of data from a hard drive to memory. That's what it says in the second line, without CPU intervention. It does it in units. How much data does it copy? The third line here says it does it in a unit called a block. We're going to talk, actually in operating system, in architecture, we talk about blocks. So you know the block size can vary, but it's a certain size.
So it's transferred
Blocks as opposed to words or bytes.
So
Blocks at a time. Main memory, you know what main memory is. You know that it's random access, means that You can get anywhere in the memory. It's volatile, which means that when you turn off the computer, it gets erased. You know that there are disks. Obviously, the disk has a disk controller. There are solid state disks. That's SSD, solid state disk. That's what SSD stands for. That's just a disk. What's the difference between solid state and a magnetic disk? Notice I made this two types of non-volatile storage. If you see the structure of this outline, two types are magnetic disks and solid state. Magnetic disks are what I call a hard drive. They spin. They have actual movement to them. And solid state are non-moving, no moving parts, which means they're less likely to break. And they're faster than magnetic disks. Nowadays, like my computer here has both. Has two hard drives. Has a large hard drive that spins and a smaller hard drive that's solid state.
The magnetic disk spins less.
It's slower. It has tracks and sectors. You don't need, I'm just telling you the main thing you need to know. The solid state has no moving parts. It's more popular nowadays. A lot of times you'll want a computer that has like only solid state memory. There are some disadvantages which are not written here. There's a disadvantage of solid state is that it has a finite number of reads and writes. You know, eventually you can't use it anymore. Or a finite number of writes. But whereas the regular hard drive is not limited, but it can break because it's moving. There's no perfect solution for them. Why is all of this is non-volatile? Volatile means that when you turn off the power, it goes. Non-volatile means even when you turn off the power, the data is still preserved. Remember, memory, like we had on MIPS, is volatile. Whatever I write to memory, if I turn the computer off, it's gone. Okay. Storage hierarchy. We talked, well, this is also an architecture. Speed, cost, there's for various parameters. Speed, usually the faster it is, the more expensive it is. There's like a little table. Like, also, the larger it is, the more expensive. So if you want it to be fast and large, it's going to be expensive. It'll be very expensive.
When you say fast anymore, the type of
Memory.
process, memory.
Memory. We're talking about
Not
memory.
what's the process.
When it says storage hierarchy there, it means memory. Well, actually, not memory. I say it wrong. It means non-volatile memory. Storage is non-volatile memory, right? Where do you store something? In a hard drive, something that's not volatile, that's not going to disappear. And then there's this concept of caching, which you're all familiar with, as a way of like buffering data. Main memory can be viewed as a cache for secondary storage. I don't know why he says this, but it's an interesting point. As you can view memory as a cache of what's on the hard drive, because the hard drive is when you turn off the computer, you're not going to have the memory anymore. You'll have the hard drive. So you cache it either into your memory. Your memory is essentially a cache. I mean, you learned about caching memory, but the memory itself is conceptually as a kind of cache for the hard drive, right? Oh, here finally he mentions device drivers, which I've been talking about. For each device, control to manage I/O provides uniform interface between controller and kernel. So there's actually, I oversimplified it. There's actually three, according to this line here, there's three levels. There's kernel, it has a controller, and the controller speaks to the device driver, and the device driver speaks to the device, right? Kernel, then there's the hardware controller, and he speaks to the device driver. I oversimplified it. to the device driver. Here, I think you're gonna see it here. No, but there's another higher. So here this you should be familiar with from architecture. Registers is the smallest, then comes cache, then main memory, then solid state disk, then magnetic disk or maker, then optical disk, which is a CD-ROM or a DVD, and then magnetic tapes. Okay,
But no.
don't have don't even have optical disk, and certainly don't have magnetic tape. Nowadays, you're just with the bottom. Yeah, but I mean, this is theoretical. Okay, caching. So you know what caching is, I assume. Caching is you first check if it's in the cache. The cache is what's also called near memory. It's nearer than the actual memory, which we talked about, because it's nearer, meaning I can get there faster. It's a faster form memory. It's also smaller. Information in use copied from slower to faster and nearer temporary storage. Okay. My battery's dying. I didn't do my charger. Right. So most systems use so we're talking about the architecture of the computer. Now we're actually really talking about computer architecture. Most systems have a special purpose processor as well. There's the general purpose processor, but the graphic card is also, I don't know if you know about like Bitcoin mining. They discovered that somehow it's faster to do the processing of the Bitcoin mining on a graphics card than on the regular CPU. That's just point, but why am I mentioning that? Just because to realize that the computer actually has multiple computers in it, multiple CPUs. It has a special CPU for the graphics card, special purpose processor. Actually, in MIPS, we didn't see this, but there's special processors to do floating point math. We didn't do floating point in the lab, but there's something called no, we didn't do floating point. Anyway. But there's a special thing called a coprocessor. It was one of the tabs on the right. There's actual other processors in it, and a special processor just for doing floating point. So we have multi-core and multi-processor. We'll talk about that in a minute more. What are multi-core programs? The multi-core refers to a single CPU with multiple execution units, while the multiprocessor refers to a system that has 2 or more CPUs. A little bit confusing, but you could have a computer with 2 CPUs, or you could have a computer with 1 CPU, but it's multi-core. It has like ELU 2 CPUs, but it's all. Yeah, I'll skip ahead. Possible to answer, but nowadays everything is multi-core. Every computer nowadays is multi-core. Where are we here? Here, I have this picture. Here, let's just look at this picture. Pictures speak 1,000 words. Yeah. So this is symmetric multiprocessing architecture. You see multiple CPUs, each with its own register and cache, and then they all access the memory. I added this. Originated in the 1960s, processors are connected by a separate bus. This line is called a bus. Operating system must support parallel processing. Right. In other words, the operating system has to know to divvy up the jobs between all the processors. That's the job of the operating system, to know how to handle that. I even go further and say my program has to be written in a way that it has multiple jobs that can be sent to different processors. Otherwise, if I just write a straight program like you did in Introduction to Computer Programming, just program that does blah, 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 and then and just a regular program, it's going to run on one of these CPUs. It's not going to run on all 3 of them simultaneously. How could it? You didn't do any parallel programming in your life yet. Parallel programming would mean creating multiple threads or multiple processes that do different parts of the job, and then waiting for them all to finish and then combining the information. So you need to have operating system support, and the programmer needs to know to use that operating system support in order to utilize these multiple CPUs. Otherwise, what will happen, the operating system will put one program on one CPU and another program on another. Each program will be on different CPUs, fine, but one program won't be spread out. That'll be good though that'll still be good if you have multiple programs running, like a browser and PowerPoint. One could be on one CPU, one could be on another CPU. Great. Now this is multi-core, the next page. Now that's interesting. No, I was saying the operating system has to know about these different CPUs and has to be able to just have a algorithm for determining who goes where, right? It has to handle that. But that's what I was saying. Whether the operating system itself is on multiple CPUs is an interesting question. It could or could not be. I mean, it could be or it doesn't have to. Now this is a picture of a dual core design. Both cores are on a single integrated circuit. That's the key point. I added that. Still requires operating system support, obviously. But it's on a single, what multi-core means, it's on a single integrated circuit. You guys know what an integrated circuit is? We call it colloquially a chip. A piece of silicon. One, you stamp it out from in a factory, and it has two cores in it. As opposed to the previous picture, each of these three things here is here, each of these gray boxes is a separate integrated circuit. Here, in the other picture, gray boxes are the gray boxes are in that one blue box, and that blue box is an integrated circuit. Obviously, dual core is, going to be faster. If everything is printed and was one thing, it's going to be better. Unless everything depends on what you actually have. Unless the CPU is a crappy CPU. If two of them doesn't help you. Okay. Now this is something, I don't know if I added this or you do benchmarking. That's the ultimate way to know anything. Van Neumann architecture. This is something that is also something, right? This is an important concept. I don't know if I added it or not, but anyway. A processing unit that contains an algorithmic logic unit and a processor register. In other words, there's something called Van Neumann architecture. This is a guy, a computer scientist from the 50s or 60s. And basically all computers now run according to this are built according to this architecture. What is Van Neumann? What is the other thing called? Turing. Did you guys learn about Turing compliance or something? No? I wonder if you'll learn about that. There's all kinds of theoretical analysis of computer architecture. Something called Turing compliant or Turing, I forget the term. You look it up, but I'm not going to talk about it. Von Neumann, though, is another person. Turing is a person. There's a Turing Award. Every year there's a Turing Award. You've heard of it? But there's a whole kind. Look up Turing in Wikipedia. You'll see there's something called, I think it's called Turing Complete. That's what it is. Turing Complete. Whatever. It's complicated. A process. So what is Van Neumann? A Van Neumann computer has the following parts. Let's start with the simplest, fourth one on the list here. External mass storage. It has a hard drive. The one up from there, memory that stores data. It has memory, which is used for both data and instructions. Well, that we know from computer architecture. Now, the one above that, a control unit that contains an instruction register and a program counter. Oh, has to have registers and a program counter. In other words, this was a chiddush. This was a chiddush to have computers that have all these things, because you could have a computer that have all these things. And what's the first thing? A processing unit, a CPU, that contains an arithmetic logic unit and registers. Okay, that we understood. Input and output mechanisms. Okay, it also should have an input. Well, here's what I added. I added this last line. The term von Neumann architecture has evolved to mean any stored program computer. Now, there's any computer that can store programs in it, as opposed to an embedded system. Like, right, embedded system might, well, no, embedded system also is stored. So I take that back. Not as close. Any computer that we can think of, any stored program computer in which an instruction fetch and a data operation cannot occur at the same time, because they share a common bus. The way the data transfers is on the bus. You learned about that in architecture, right? Remember you learned about a trinary, a tri-state device that allows things to pass on the bus. Only one thing can go on the bus at a time. So if you think about it, I have data in memory and I have code in memory. So I want to retrieve a line of code, I have to use the bus. I also want to retrieve a line of data to do an action. I have to read from the bus. So the bus is going to create a bottleneck. This is referred to as the von Neumann bottleneck, because I can't do two things at the same time. I can't read an instruction. And did you guys do pipelining?
Yeah.
So I think that in pipelining, you couldn't do the instruction fetch part at the same time as you're doing a data part, right? That's this bottleneck that we're talking about. But anyway, the term von Neumann architecture has evolved to mean different things. But those 6 things that we listed is what it has to happen. What's the alternative? That's a good question. I have to think. I don't know. To think about that. What would be a computer that's not von Neumann? It wouldn't have some of those things. It might not have registers, or it might only have registers. It might not have data. Anyway, anything that would, I don't know if I can't think of an example of something like that, but that would be a good thing to think. What? No, it's not. Multi-programming? No.
And the CPU and I running.
Yes, that's true. Right. It could do something else. Wait, let's here. What did I write in bold? What is multi-programming? Multi-programming, first of all, is an old-fashioned concept. And we're just going to mention it to contrast it with time sharing. These are actually, now we're talking about architecture up to now. Now we're back to more operating systems. That was like computer structure. Now we're back to operating systems. So this is like, it's like, what is multi-programming? It means you can have multiple programs on the same computer. Multi-programming, 2 programs on the same computer. Simple. When does one program run and the other one not? So in multi-programming, when a job has to wait for IO, the CPU is now idle. So the operating system switches to a different job, to a different program. But it will not, if the program does not use any IO or very little, let's say it's computing pi to the 10,000th decimal place. So it's going to take it weeks to run, and the end it's going to have one little printout. So in multi-programming, it will just keep running for weeks, and the other program will wait until eventually it goes to IO, and then he'll get there, and then he'll get there. So that's multi-programming. What is time sharing? Time sharing is that even if you want 2 weeks of the program, I'm going to stop you after 10 milliseconds and give 10 milliseconds to the other guy. And then 10 milliseconds later, I'll come back to you. And I'll do a kind of alternating behavior based on what we call time slice. All right, that's the general thing. Now I'll just go to the bullets here. What's here? So time sharing, yeah, this is a question that I could be on the exam for sure. What's the difference between multi-programming and multitasking? Time sharing is also called multitasking. But time sharing or multitasking means that it has a time slice called a time slice. And based on the time slice, it interrupts the program, whether or not it's in IO. Whether or not the program has gone to do an IO and has left the CPU idle. In multi-programming, it only switches between programs when the CPU has gone idle because of an IO operation. Now, that said, I should add, very important point, that in time sharing, you will also interrupt if there's an IO. So in other words, if a time slice is 10 milliseconds, but after 5 milliseconds, I wanted to print hello world to the screen. So I went to IO after 5 milliseconds. The other program will jump in and take the CPU. He won't get 15 seconds, 15 milliseconds. He'll get it still 10, but he'll start earlier. So there are two parameters to interrupt a process in time sharing. Either the time slice is finished or I've gone to IO. And what did I write here? What did the book write? Response time should be less than 1 second. Response time means that if I hit if I type enter, if I type hello and I hit enter, it shouldn't take more than a second for me to get the response. Each user has at least one program executing memory. Yeah, wait, third point here is if several jobs are ready to run at the same time, the CPU has to do scheduling. Let's say I have 10 programs running. Each one gets 10 milliseconds. So how do I go? The most simple idea would be what we call round robin. I do the first one, second one, third one. When I get to the 10th one, I go back to the first one. And I keep going very fairly. There may be other ways. I may have priority. There are other possible things. That whatever decisions I make, that's what we call CPU scheduling. Get a question? No, because multi-programming only switches when there is an IO. In other words, time sharing is a kind of multi-programming, which has an additional factor to interrupt, which is a time limit. No, going to IO means that the process is now involved in IO and has therefore allowed the CPU to be available for anybody else. So the operating system will be aware of that and say, oh, I got a free CPU, I'll give another process to run. That's going to happen whether it's multi-programming or multitasking, time sharing. The only additional thing is that in time sharing, even if I'm busy using the CPU, I'm happily using it. The operating system will come in and say, stop what you're doing. I'm taking the CPU away and giving it to somebody else. For IO, for sure. If I went to IO, if the other program is in IO? I don't know what you mean by that. IO is a time when we don't want CPU. We can think about programs as essentially having two states. Either they're CPU intensive or they're IO intensive. Either they're using the CPU or they're using the device. But they're not doing those simultaneously. Whenever they're using the device, the IO input-output device, so the CPU is available. So, because they can't use both at the same time. So therefore, I can give the CPU to another program. That's what multi-programming does. But also multitasking does that. They both do that. So what's the difference? The only difference is that if you try to hog the CPU by calculating pi to the 10,000th decimal place, and you want to have the CPU for 2 weeks, well, we're not going to make all the other programs sit around waiting. We're going to interrupt you. That would be time sharing. That's why it's called time sharing, because the word time means we put a timer on you. We give you a maximum of 10 seconds. It'd be kind of like an ideal, think about the ideal supermarket. How does supermarket work? You get there, and when the guy finishes, he no longer needs it's not really multitasking. Let's think about it. It's keyless multitasking. He no longer needs the clerk who's checking the checkout clerk. Now he comes in, he gives 10 items, and now you come in, and then somebody else 10. Eventually, it's your turn, and you get the CPU. You get the checkout clerk. But imagine now that somebody comes in front of you. I got 10,000 items to buy, and this woman behind me says, "I only have 2 items. Can I go in front of you?" So I say, "Sure, go in front of me." Now, another person comes, and I say, "Oh, I'm sick of people going in front of me." That's it. Actually, I have a rule. I let one person go in front of me. Second person, I say, "No, I already let somebody go in front of me. You have to wait." It's a good rule because then you don't have to have a moral dilemma every time. But imagine a different system. Imagine a system where after 10 items, she automatically stops and lets the next person come. Person behind me comes, and he's got also a huge cart full of 10,000 things. So he gets 10 items to go through. Now the next person behind him goes. She's only got 2 items. She gets to go. And she's finished. Now she's out of the queue. Now we go back to me, and I do 10 more of my items. Go after the guy behind me, 10 more of his items. So that's time sharing, where if I'm finished, so I'm finished. But if I'm finished with the clerk, then I'm finished. But if I'm not finished, I'm going to be stopped anyway after 10 items. Well, it's not 10 items here, it's 10 seconds. And finished is not necessarily finished. Finished just means I'm finished for the moment. I'm going to come back to the CPU later. I'm doing IO now. I'm doing something else. But I might come back to the supermarket and buy more goods. But right now, I'm going to go to the car and put stuff in the car. And then I'm going to come back to the store and buy more stuff. I'm constantly interested in using that clerk. But at the moment, I'm finished. Yeah. Yes. Yes. Excellent point. Excellent point. Yes. Switching between this. Now, all of a sudden, I go jump to the guy behind me with the 10. So it's called context switching. The term is called context switching. That's what we call it, switching. And it takes time. There's an overhead. We call it overhead. And if the overhead is very large, then it's not worth it. So the idea of multi-programming was to say, well, maybe the overhead is very large. Let's just do it when we really need to, right? But we're not going to interrupt people just stop. Only if they're doing IO and they really don't need you, then we'll drop. Okay, let's go on.
Swapping is like also what you were saying that.
If a process didn't, oh, this is like we're like touching on major topics that we'll talk about. But yes, if a process didn't fit, if processes don't fit in memory, swapping moves them in and out to run. Yeah, that's just saying, like, what if my memory is 1 gigabyte and my program is 2 gigabytes long? How do I run? I theoretically put the whole program into memory. So swapping just means I put in part of the program and put out. It's also called virtual memory. Virtual memory allows execution of processes not completely in memory. Right. We'll talk about these topics in greater depth later. All right, so here's a nice little picture. It just shows you that there are multiple jobs. The operating system is also a job. It's also using memory. And all these jobs, those are programs. And they're in memory at the same time. Let's go on. Okay, as we already said, operating systems are interrupt driven. Division by 0 requests for operating system service. Now, if your program is a big question, or it's a question in my mind all the time, is division by 0 and what kind of it's an interrupt, right? You divide it by 0 on some. It depends on some computers. The hardware itself will detect that you divided by 0 and send an exception, and the operating system will receive that and stop your program. All right, that's interrupt. We're just operating system operations. These are things that it does. Other process problems include infinite loops. We don't want processes to have infinite loops. We don't want them to modify each other without permission. We don't want them to modify the operating system. We have to have security. An operating system has to have security, which means that one program doesn't modify another program. one way of having some kind of security is to have what's called dual mode, which is user mode and kernel mode. Most of the time, your program will be in user mode, which means regular permissions, limited permissions. When it needs to access something, it will go into kernel mode. And then it will run the kernel program. Well, let's say you want to access the hardware. You want to write to the screen. The only way you can do that is if you're in kernel mode. And of course, you'll be doing it through code written in the kernel. It's a little bit weird concept. What's going on here is you think, I'll say it like this, you think your program, when you say your program is the only thing running. All right, let me say it differently. When your program is running, it's called a process, right? That's what we call it, a process. Is your process going to only be executing the lines of your code, or will your process also do other things than your code? So you might think, well, my process is going to run the lines of my code. So it's my program running. That's the process. But the minute you ask the operating system to do something, what actually is going to happen is that your program is going to execute lines of the operating system, code written, operating system lines of code. Your process will do that. And it's not like your process will stop and wait and tread water until the kernel does something for you, until the operating system does something for you. No, your program itself will run the kernel code. So let's say read the screen or write to the read the screen or write to the screen or read from the keyboard. But when it does that, it will be in what's called kernel mode, so that it'll have permission to get to the screen. So in other words, if I try to write to the screen without calling a system call, so a system call will do two things. A system call that can write to the screen, hello world, will do two things. It will stop my execution of my code and start execution of kernel code. And it will also put me into kernel mode so that I can succeed at running those lines. If I would try to access in other words, like this, if I would be a very smart hacker and I would say, I'm going to try to write to the screen without using a system call, the operating system would not let me, because I would not be in kernel mode. Even if I knew the right lines, the right machine language code to get to the hardware, I still wouldn't succeed because the operating system I would not be in kernel mode. That's the idea. You have to be in kernel mode when you're executing the kernel. Sort of logical. So there's a mode bit provided by the hardware. So the hardware will detect, oh, wait a second, are you in kernel mode or not in kernel mode? System call, here in bold, I wrote system call changes mode to kernel mode. Return from call resets it to user. That's the key point. The key point is that when you're executing some system call, you're also having to go into kernel mode, and then the hardware will see that you're in kernel mode and allow you to access it. Increasingly, CPUs support multi-mode operations. Whatever, I don't know what that is. Yeah. Yeah, cout is going to request a system call, yeah. And here you just see a simple picture. I'm running along here, user process execution. Oh, I do a system call. The arrows is my process. You have to think of the dark arrows is the behavior of my process. My process goes into kernel mode, into the blue area, executes the system call, and then returns back to the user mode and continues on its merry way. It's a weird concept it's hard to understand that. You really want to think, your mind wants to think, no, the kernel is doing the system call. So what we're saying is, no, you're doing the system call as the kernel. It's like you took on his clothing. Yeah, just a second. Yeah. No, kernel is the operating system. The operating system. The operating system, it has a bit that tells it that he's in kernel mode. That the operating system says, I'm in kernel mode. And then the hardware will allow it to access it. Okay. How are we doing? You have more slides. We're getting near the end. Yeah. I have 12, so I guess we have extra, but okay. Process management. A process is a program in execution. I've been saying that all the time, right? Process is a program in execution. Because a program just sits in memory, it's not a process. It is a unit of work within the system. In other words, you can think of an operating system as having lots of processes, and it wants to run them all, give them all as much service as it can. Service means giving it resources, like the CPU is a resource. Throwing out all the terminology of the course, right? Giving it resources. A resource is the screen, is memory, CPU time. Usually we think of it as memory and CPU time. Process need resources to accomplish its tasks, like CPU, memory, input-output devices, and files. Those are all types of resources that the operating system can provide. Resources is like, right? The school provides me with markers that I can write on the board. Those are resources, things that I need. Process termination requires reclaim of any reusable resources. In other words, when the process finishes, the memory space that was assigned to him has to be put back into the general pool for other processes. So for example, if you remember your program, your core, I always like to compare it to computer architecture, because there you had this huge amount of memory and you could write anywhere in that memory. All of it was yours. Now we're going to say, no, we're going to have 1,000 programs and each one gets a certain slice of the memory, and you're not allowed to write anywhere that's not yours. The operating system will have to maintain tables for each process where its memory starts and ends. And it could be fragmented. It could be that it has a piece of memory here and a piece of memory there and a piece of memory there. And they're all related to the same process. So the operating system has to know and keep track of for each process where its memory is. And this line we just read is saying it has to free up that memory when the process finishes. That's just one example. I just said memory. Obviously, I mean, registers is the same thing. Files also. If I have registered that a file is being accessed by a program, the program finishes, I'm going to say no, it's no longer accessing this file. Okay, so now we're going to start talking about threaded. See, the book just, I mean, this introduction is like throwing out all kinds of concepts, and I'm trying to explain them all as we go. But we're going to go in greater depth about this. Yeah, this is like a survey of the whole course. Exactly. You don't have to get everything that I say now. For example, threads. Because now process management is chapter 3, which we'll get to. That's actually like one of our favorite parts of the course, or the main section of the course. Single-threaded process has one program counter specify the location of the next instruction to execute. Right. what you're familiar with is what you did in computer architecture is single threaded programs. It has one program counter. Process execution instruction, it executes instructions sequentially, one at a time until completion. Multi-threaded process has one program counter per thread. So if you have multiple threads, each thread has its own counter. But what's going on is, what do I mean its own counter? It has the same program. In other words, the program code is identical, but there's like two different pointers to the code. One process is up here running these lines, another process is down here. And maybe this one will get here and then this one will jump up here. You know, their PCs are in totally different locations, but they're in the same program. So we can't call it two programs, it's one program, but it has multiple threads. Typically, system has many processes, some user, some operating system running currently. Right, if you open up an operating system, you'll see that it has many processes running. Some are the operating system and some are not. Next. Process management activities. This is what the operating system has to do to manage its processes. It has to create and delete both user and system processes. It has to stop and restart them, suspend. It has to allow synchronization, which we call mutex. You're familiar with the concepts of mutex? So we'll talk about that. Mutex is shorthand for mutual exclusion. In other words, if I'm writing to a file, maybe you shouldn't be writing to that same file. But if I'm reading from the file, you could be reading from it. So there's mutual exclusion for writing, but not for reading. Provide mechanism for process communication. I have two completely different processes. And they're not even having, not the same process, two completely different processes, two different programs, but they want to communicate on the same computer. So there's mechanisms for that. That's called sockets or pipes. Providing mechanisms for deadlock handling. Deadlock, we'll talk about deadlock, a chapter on deadlock. Deadlock means like, what if I have, let's say I need two files to be opened to do my work. I want to read from this one and write to that one. And the other process also needs two files to be opened, the same two. And I have one of them and he has the other. I'm waiting for him to finish so that I can get the second one. But he's waiting for me to finish because he wants the second, he wants the first one. So we're each waiting for each other and we're each holding half of what the other one needs. So that's a deadlock. Nobody can progress. There's no progress because there's hold and wait. It's called hold and wait. So a good operating system might prevent that or might resolve it if it occurs. I added this, copy on write. Sometimes referred to as implicit sharing or shadowing, is a resource management technique used by operating systems to efficiently implement duplicate or copy up. In other words, if I have a process and I want to make a copy of the process, now I want two processes to run. Now he has they're going to copy all the data. So I made an array called hello with the data in it, hello world. And now I made a copy of this whole process and I'm going to run it also. Now, should I make a whole copy of that hello world? Well, logically I should, because maybe he'll change it. I don't want, he's not going to change it. They each have their own copies of that thing. He was a copy, but from now on, he'll run with his own version of everything. So there's a concept called copy on write, which means, you know what? Make the new process. And if he doesn't touch that array, hello world, then just let them share it. The minute he wants to touch it, then quickly make a copy of it and let him copy his own. What this gains for me is that I save memory. And I also, even more important, is I save time in the creation of the process. When I wanted to create the process, I can get them up and running quicker because I don't have to make all the data. And I only have to create, and only on the fly, as the data is being written to, this is an efficiency issue of how to create multiple processes Okay, that's. Oh, yeah. Okay, so we'll stop here. Sorry, I was late today. So good, we stopped at a good point. Memory management. We may. Tuesday is a Tirgulo. You know what I'm gonna do? I hope this is not mean. I'm gonna start the next slides next time. Because the rest of it, like I said, it's really just a survey of what we're gonna be doing later. So you can, if you can look it over, but we'll get to it in greater depth. Oh, I had a girl, Tamar Harizi.